Okay, welcome students. Welcome to the video on AEC prerequisites 3. So in this series, we have actually asked you people to find the region of operation of BJT for different cases. So that is, we are asked to find whether the BJT is operating in cutoff region, active region or saturation region. We actually ask people to assume the value of beta as 100, VBE as 700 millivolts, and one more parameter IS was given as 1 into 10 power minus 17 amperes. And of course, so we have been given 5 different circuits. And of course, there are different reasons for giving all these circuits, and you may be a bit surprised to see you have been given an extra parameter, that is IS, in this particular example. So let us try to understand how do we solve all this, and how does these assumptions are true, and how can we just continue with all these things. Okay, we have been given some assumptions as 1 into 10 power minus 17 amperes. This is IS. We will also talk about what is this IS, and we have been also given, or we have asked to assume the VB of 700 millivolt and the beta, which is IC by IB, so is assumed to be 100. So with these assumptions, let us try to find the region of operation. Before we continue there, so let us try to understand the 3 regions of operation of the BJT. So we have 3 terminals of the BJT. Okay, if I write it so here, this is the symbol, this is a NPN transistor, so naturally this becomes NPN. Suppose if you consider this as emitter, this as base, this as collector. If you can see, there are 2 PN junctions. If you name them, so there is one PN junction and there is another PN junction. This is called as collector base PN junction. This is called as emitter base PN junction. So there are 2 PN junctions. So this is also PN junction, this is also PN junction. One is emitter base, other is collector base. Now, since there is a PN junction, so naturally you can think of PN junction which is like a diode. So if this is P and N, we will always talk about the forward bias and reverse bias whenever you have a junction. So we know that if you have this type of polarity of the battery, if the positive is going to P and the negative is going to N, meaning if P is more positive than N, then we'll call it as forward biased. So this will be like forward biased. This is forward biased. So when it comes to the situation where you have a P material, N material, there is a PN junction. If it happens so, now you have P is getting negative and N is getting positive. Suppose N is more positive than P, then we call it as reverse bias. So then we call it as reverse biased. So this is a reverse biased. So now, since we have 2 such PN junctions, we are looking at whether it is forward biased or reverse biased, and there are different combinations. Now we will take the output characteristics of the BJT, so which refers to output voltage VCE and output current IC for a given value of IB. So now assume that, okay, this is how it goes. This is for a given value of IB. Now so here we have 2 regions of operation. This is, okay, this region is called as active region, and this region, typically this region is called as saturation region. So if I write it, saturation region. So when it comes to cutoff, so where cutoff is, okay, now the BJT will be off, so there is no IC, so this is your cutoff region. So cutoff region where IC is equal to 0, which is of course a relevant case where you don't have a collector current at all. Since we have PN junctions, as you can see here, so this is one PN junction between collector and base. So this is, so I can write a diode like this, I can write a diode like this, I can write effectively a diode like this. Suppose if this potential is more and this is less, then it is reverse bias. So as we know that if N is having larger potential than base, then it is reverse bias. That is, if I say this is the voltage at collector, this is voltage at base, suppose voltage at collector is greater than voltage at base, then I'll say CB, collector base junction, is reverse biased. That is what is, if collector base junction needs to be reverse biased, then voltage at the collector should be greater than voltage at the base. Now, same collector base junction will be forward biased if the voltage at the collector is less than voltage at the base. So suppose that this voltage is less than this voltage, so which is obviously, so then when this voltage is more than this, when voltage at base is more than voltage at collector, or otherwise if voltage at collector is less than voltage at base, that is voltage at N is lesser than voltage at P, which is what is seen here. Voltage at N is lesser than voltage at P, then it is forward biased. You can see this is what is forward biased. So now this is about collector base junction. This is what is this junction. So next is emitter base junction. Again, when it will be reverse bias, when it is reverse bias, so now of course you have this reverse bias means, okay, this should be more than this, so VE should be more than VB. Suppose if the emitter voltage is more than base voltage, then it is reverse bias. So the same emitter base junction is forward biased if VE is less than VB. That is, or you can say when VB is greater than VE, when voltage at the emitter is more than voltage at the, voltage at the base, this is base, no? Voltage at the base is more than voltage at the emitter, then it is forward biased. So now you have two junctions and four possibilities. So reverse bias, reverse bias, reverse bias, forward bias, forward bias, reverse bias, forward bias, forward bias. So there are no four different combinations. Actually we have only three combinations. That is, if collector base junction is reverse biased and emitter base junction is forward biased. So for transistor to operate, emitter base junction has to be forward biased. So if it is forward biased, then if collector base junction is reverse biased, then we will be operating in region is active region. So what do you mean by collector base junction reverse bias? So collector, voltage at collector is greater than voltage at base. So for this to be forward biased, voltage at base is greater than voltage at emitter. We'll just come to all these things. This should not be get confused. So unless you are thorough with this, then all these things understanding is will be shaky. So make sure that you are getting when it is forward bias, when it is reverse bias. So it is very simple. Voltage at P terminal, P side of your material should be greater than N side, then it is forward bias. That's what is this. P is greater than N, forward bias. If P is less than N, that is potential, then it is reverse bias. So this is active region. So again same. Okay, now again same collector base junction. So collector base junction is forward biased. This is also forward biased. So then it is saturation. So what do you mean by this forward biased? So what do you have here? This is NP, which should be more now? P should be more. That is VB if it is more than VC, or collector voltage if it is less than base voltage, then, and of course this base voltage has to be more than emitter voltage, then it is saturation. So when it will be in cutoff, it will be in cutoff if, of course, irrespective of this, irrespective of collector base junction, if emitter base junction is reverse bias, this is your emitter base junction. If it is reverse bias, then gone. This is in cutoff. Whether it is, of course, when it is reverse bias, that is when this is reverse bias, there is no question of this whether it is forward bias or reverse bias. It's in cutoff region because no current flows. So this can be either forward bias or reverse bias, because this doesn't come into picture at all. So this will not come into picture at all because this voltage will not be always, of course, will be always 5 volts because no current flows, all voltage will be available here. So this will be always, so your N will be always at a higher potential, it will be always reverse bias. So both will be reverse bias, so you will have cutoff region. So majorly the emitter base junction should be reverse bias, so then it is cutoff. Okay, keeping all these things in mind, let us consider this. Let us take up this example and try to find out what is the region of operation of this. So before we actually go into that, so we have three different, a few equations to understand. One of the equation is what is IB? What is the relation between IC and IB? So IC is equal to beta times IB, where beta is current amplification factor in a transistor. This is beta. And we also have one more expression for IC, collector current, in terms of VBE, that is IS into exponential VBE by VT. VBE by VT. Of course, the exact equation, this is a slightly approximate equation. The exact equation is IS into e power V, of course, e power is nothing but exponential by Vt minus 1. So this is the exact equation. Since this quantity is very, very large, so we will just neglect this term, so that IC can be written as IS e power VBE by Vt, where Vt is thermal voltage, given by Kt by Q. K is the Boltzmann constant, T is temperature in Kelvin, Q is the electron charge, which will be for a temperature of 23 degrees. For a temperature of for T in centigrade, if it is 23 degrees, then Vt comes out to be 26 millivolt. We call it as thermal voltage. At room temperature, the thermal voltage is 26 millivolts. So we actually have two equations which are defining the collector current. One is depending on the value of beta, other one is depending on the value of IS, and of course VB, IS and VB. So now we'll be knowing, why we are given this IS also into picture. Now, so let us take up the first case. That is prerequisite. Let us jump and try to find out what are the currents, and we will also verify that using simulations whether our calculations are correct or not. So this is 5 volt given, this is 100 ohm, and this is given as 100k, this is so and so. Now we need to find what is the value of IB here. So if I say this as VCC and this is VBE, shall I write IB as equal to VCC minus VBE by RB? So let me take this as RB. So what is this? It is 5 minus 0.7 by 100 kilo ohm, which happens to be, just a minute, it is now 4.3 divided by 100 exponential 3. So this happens to be, now always put the value of current in either milli or micro. The moment when you do 4.3 divided by 100 exponential 3, if you say equals, it will come as 4.3 into 10 power minus 5. Never write the answer as 4.3 into 10 power minus 5 ampere. Please don't write it, because we engineers will always write the quantities in either kilo, mega, milli, micro, giga, nano, pico. These are the engineering quantities we are going to measure. There is no specific name for 10 power minus 5. So instead of that, so if you go to your Calc, whenever you get this answer, please press ENG. That's why this is given as ENG, that is engineering. If you press ENG, can you see that 4.2 10 power 4.3 into 10 power minus 5 will become 43 10 power minus 6. So what is IB? It is 43 microampere. This is the value of IB. So then what is IC is equal to, we know that it is beta times IB, which is nothing but into 100. So can you see now it is 4.3 milliamperes. It is 4.3 milliamperes. Now, so this is the current that is flowing. So IC is equal to 4.3 milliamperes. So I should know what is the voltage at VC. So what is the voltage at VC? This is nothing but this VCC minus the drop here. So drop across IC and RC. Drop across this resistor. This is, let me name it as RC. So what is this now? Is it not 5 minus, how much is IC? It is 4.3 milli into 100 ohm. So can you see it is 100, okay, minus 5, okay, I'll just make it, this is equal to 4.57 volts. Can you see now how much is the voltage here? It is 0.7. How much is the voltage here? 4.7 volts. So 4.57 volts. Correct? So what is the region of operation? Now let us now decide what is the region of operation of this MOSFET. So we know that for MOSFET to be in active region, so emitter base junction should be forward bias. So what is the voltage? Okay, let us write what is VB, PE and VC. Let us write what is collector voltage, sorry, base voltage, emitter voltage, collector voltage. Is the emitter voltage 0 volt? Because emitter is grounded. What is the base voltage? Is it 0.7? What is the collector voltage? Is it not 4.57 volt? It is right. Is the collector voltage more than base voltage? If the collector voltage is more than base voltage, is your CP reverse biased? So is your base voltage more than emitter voltage? Is your emitter base, is it not forward biased? Because emitter is at low potential than collector, than base. So emitter base junction is this junction is forward bias, this junction is reverse bias. So this is in forward bias, please. Forward bias. Okay, this is theoretically with the values that we know, or what the equation that we know. These are all, again, lot of assumptions are made. In terms of VB. So that's a big assumption that we are making. Okay, let us move to next one. Next one is something like this. Again, similar type of thing. Only thing is that this is made. Okay, let me just redo it here. The second problem is this is now replaced by 10 kilo ohm. Correct? So that is replaced by 10 kilo ohm. The moment this is replaced by 10 kilo ohm, does your IB remains same here? IB remains 43 microampere. This is remaining same. And does how about IC? IC also remains same. But what is this? Okay, now this remains same here. Now it is 5 minus 4.3 milliampere into 10 kilo ohm. 10 kilo ohm. So what is expected now? It is now 5 minus 4.3 exponential minus 3 into 10 exponential 3. Oh, see, now you have minus 38 volt. This is highly impossible. Okay, why something like this? Okay, suppose if I ask you to write it, so you will just simply write, okay, this is as per equation, this is so, this is minus 38, you say it as now you cannot conclude now, because what is voltage at base? Voltage at base you assume it as 0.7, voltage at emitter is 0 volt, voltage at collector is minus 38 volt, which is something what you never thought of. Now you start wondering, okay, why it has happened so, why it has happened so. Correct? So now this is okay. So what we had, okay, now this is the thing. So when you have 38 millivolts, so what is the region of operation of this now? So let us not worry about this now. So let us go to next one. So we will say, we'll just drop it at this point. Suppose if it is an examination question, we'll just say that we'll just say this is forward bias, then you say this is actually minus voltage is lesser than this, is it not? So then is your base is more than collector, is the base is more than collector, then you say this as forward bias, then you say it is in saturation region. This is in saturation region. But what is the current flowing? Is the same amount of current flows? Is the same amount of current flows? Let us see what happens. Let us see what happens. Fine. Now let us move to the third one. So we'll just come back to this. So don't panic. So let us come back to this. Let us do a simulation, and that's what is the difference between when you have it as 10K, when you do it using calculation, you just end up there and then saying it as saturation, because this minus 38 is not a valid answer. This is not a valid answer. This much amount of voltage drop can never occur here. So because the voltage minimum is 0, the voltage can never be more than 0 here. So this is okay, it cannot be more negative than 0. So minus 38 is not possible. But equation wise it is coming out to be minus 38. You are just following the equation, then writing the value. We'll come back to this when we do the simulation. Let us try to understand what are the limitations of these equations. In simply substituting and getting some answer is not the solution. Suppose what you did in the earlier case, you assumed it as 0.7, you got some voltage and then did so and so, and then you are having these things. So let us see what happens when we actually do the simulation. Let us see the third one. So what is the third one? Third one goes like this. This is the third one. You can see this is very simple one. What I have this here. This is grounded. This is 100K. This is 5 volt. This is 5 kilo. This is 5 kilo. Fine. So now, what is the current now? The current is 0. So this is current is 0. When IB is equal to 0, then how much is IC? IC is also 0. When IC is 0, so how about this? This is reverse biased. How about this? This is also reverse biased. So now, when both are reverse biased, you can certainly see this is in cutoff region. Cutoff region. Fine. So these are the values of, these are the operating regions of the first three circuits, which is a fixed bias. Okay, we'll come to this later. Over here it was in active region. Over here we somehow wrote it as saturation region, and here you expected minus 38 volts, which is not a possible solution, and you have this as, of course this is cut off because there is no base drive at all, there is no base current, so no collector current, so it is in off condition, off, saturation, active. Okay, this is the thing. So what are the assumption? VB is assumed as 700 millivolt and beta is 100. We have not touched this, we have not used this IS so far. So now let us do the simulation. So if I go to simulation, okay, now let me take this simulation. Okay, let me have the same circuit here. So here you have an NPN transistor. Can you see this is an NPN transistor? Okay, this is NPN transistor. I can place it here. So then I want to have a resistor. This is a resistor. I'll put this. I need one more resistor. Fine. Then I'll put a battery which is there in miscellaneous. So here there is a battery. I'll put it here. Okay, there is one extra battery coming. Let me just delete them. For deleting, you can select this. Okay, let me select this. this is gone. Okay, there are two placed here. Let me name it as VCC. Let me make it as 5 volts, and this resistor is first 100 ohm. Let me name it as RC, and let me name this as RB, and its resistance is 100 kilo ohm. Done. Let me do the connection. I need a ground also. Let me put ground here. So let me wire it. Okay, I'm connecting this to this and then to this. Then it is coming all the way down here. It goes here, goes here. From here it comes down. This is again connected here. This will go to base and 5. Okay, now this is RB, RC, so on so. So what is that we need to measure? We need to measure this current and this voltage, so that we can see what is the. So now what we'll do? We will do. Okay, I will take. Okay, I had to do analysis. So the analysis now is I had to configure. So transient I'm going to configure. Okay, that need to be done. It is 1 millisecond. Then it is 0, then it is 1 microsecond. Okay, this is a transient analysis I am doing. Now if I run, okay, now I'm already there. I can actually run it. So I want to see what is the current. See here, this is if you once you run it, so you have these parameters. You can actually come to the circuit and place your mouse close to that. You can see there is a current indicated going down into the base. This is my base current. If you can actually see, the base current we calculated was how much? The base current that we calculated was how much? Sorry, for the first case it is 43 microampere, because you assumed it as 5 and this is 0.7 and this is 100k, so on. So we are supposed to get 43 milliamperes. Let us see how much is the current that we are getting. Okay, we are getting a current of 41 point so on so. Now, okay, majorly before that we need to do one more parameter. So if you can see here, now this is a transistor what you have taken, but how about these specifications? So here in the specifications we actually said, okay, this should have a IS of 1 into 10 power minus 17, VB is this and beta is this. Actually, for a transistor you cannot specify VBE. VBE is not a parameter that can be specified. Only thing that you can specify is beta factor and IS. So how do we specify that? Those things can be specified in the SPICE simulation by using a directive. You can see this is, can you see this is SPICE directive. If I select this, now I can say this transistor should have the specifications as required for my simulation, which is beta of 100 and IS of 1 into 10 power minus 17. So it is dot model comma space npn space npn. So this is the model I'm defining it for this transistor Q1, which is a NPN transistor. Open the parenthesis, say it as beta BF. Beta factor is 100, comma, you have to say IS is 1 e power minus 17. So you are actually specifying two values of this transistor, which is beta F, which is beta factor, and IS, which is 1 into 10 power minus of 17. If I click on this, now this transistor, like you had this transistor, no? You should have this transistor, a IS of 1 into 10 power minus 17 and beta of 100. So that's what we said here. Now what is this IS? IS is actually reverse saturation current in emitter base junction. In this emitter base junction, when the transistor is reverse bias, so there is a current. This is a leakage current that is going to happen in base emitter junction. This is of course beta factor. This is the model for this particular transistor. Now let me run it. So now this is the current that I'm having. This is the current that I'm having. You can see this is 41 point so and so. Now let me measure how much is VBE. So VBE, now we assume that it is 700 millivolt. You can actually see how much is VBE. Can you see now how much is VBE? VBE is actually 870 millivolts. So it's not 700. It's not 700 millivolt. It's actually 870 millivolt. 870 millivolt. So now, if you do 5 minus, suppose if you do 5 minus 870.46 divided by 100, it is 5 minus 870.446 milli divided by 100 exponential 3. Can you see the current is 41.2? That's what you have here. You can also see here. Can you see the current is this much? I'll put it as ENG. Can it is 41.36? You can just see here. Does the same current flows here also? Can you see it is 41.2? It is 41.29 milliampere. So IB is this much. Can you see IC now? Since we made the beta of this is 100, then IC has to be naturally 100 times of this. So where is 100 times? So let me see here. See this I of RC, is it not 4.12 milliampere? Can you see it is 4.12 milliampere? Then how much is this voltage? Voltage at collector. This is voltage at collector. So let me label this as collector voltage. So how do I label? Go to this label net. I'll say it as VC. This is VC here. You can name this as VB. I can name it as VB. This I can delete. For deleting, take this scissor and cut. Now if you run again, can you see now this is okay, let me just delete this. Okay, I can delete this. Okay, let me again, I want to see the voltages here. Sorry. Now let me see the voltage. Okay, this is the voltage. You can see this is VB, voltage at base, and this is voltage at collector. The voltage at collector, I can see 4.58 volts. This voltage at collector, which is far more than voltage at base, so it is reverse bias. So it is reverse bias. How about this? This is forward bias. So this is in active region. This is in active region. Meaning, if I come to this, so what is the value of VC you have? Almost 4.5 volt. This is assume that if it is 5 volt, this is 4.5 volt. You are somewhere here, and collector current is some 4 point something milliampere. So you are operating here. This is active region. This is active region. Fine. So let us go to make this as 100K. Let us make it 10K. That's what is our second question. No? What is the second question? Second question is where is that? Okay, here. Our second question, we replace that by 10K. When you replace it by 10K, let us see what happens. So let us see whether this is minus 38 or not. So now let me make this 10K and then run. Let me again run. Okay, let me just okay, before let me just run it. If I run, if I see what is this base current, is the base current same? Can you see now the base current is 41.8 microampere. How much is this current? Can you see this now? It is, how much is the current of IC? It is this much. It is this much. Why it is this much? Why it is this much? Because we know that if you actually find the ratio of IC and IB, so So suppose let me write those two currents. Let me take one here, or let me just delete these two. Okay, clear. Okay, what I do is let me delete this, add. Okay, add traces, one corresponding to base current. Okay, other corresponding to, where is that? Add traces, collector current. Okay, now see, now this is my base current. See, now these two are the currents. One is base current, other is collector current. So IB is equal to 41.8 microampere and IC is equal to 492.8 microampere. So there is one very interesting thing you should understand here. See here, we have these as the current values. This is the value of IB, which is almost same when this was 100 ohm. When this was 100 ohm, the same IB was flowing, but you can see what's the value of IC. IC is not 100 times of this. What is 100 times of this? 100 times of this becomes, what is 41.8 exponential minus 6 into 100 is actually 4.18 milliampere. This is 4.18 milliampere, but actually current flowing is 492 microampere, meaning since the transistor is not operating in active region, this equation IC is equal to beta times IB is not valid for all cases. So suppose now, since the value of beta is 100, this equation is not valid whenever the MOSFET is operating in this region. See here, for this region IC is equal to beta times IB. In this region IC is not equal to beta times IB. This is not always, because you are operating here, correct? So this, whatever you got, minus 38 volt is not correct. Actually, how much is the voltage that you are getting? The voltage that you are getting at this collector point is how much? This is VC. How much you have? You have VC is 71.11 millivolt. What is the voltage at base? Shall we know what is the voltage at base? Voltage at base is, this is voltage at base, which is 819 millivolt, and of course voltage at emitter is 0 volt. Now with these specifications, what's your conclusion? Can you see the collector voltage is more than base, the base voltage, is it more than collector voltage? So is your collector base junction, so directly like this, no? This is N, P, N. So P is at a higher potential compared to N. Is this is base, this is collector. Is this base voltage more than collector voltage? So it is forward biased. How about this? This is 819, this is 0. Is this also forward biased? So both are forward biased. So when both are forward biased, we know that this is in saturation. In the previous case also we said that this may be in saturation, but this was a huge mistake, that if at all if you make it as minus 38 volt, it is wrong, because you cannot take this as so and so, because IC is not equal to beta times IB for all operating regions. This is only true for when the BJT is operating in active region here. That is, when it is operating here, it is beta times IB. Here it's naturally less. Can you see the collector current is less? It is less. So then beta of 100 is not valid here. Beta 100 is valid only in this active region. Okay, let us also see what is the IC and VB stuff. So maybe we'll just verify how much is the value of IS we have considered. We have considered IS of, so let us, so in this particular case, suppose if you see here, let me just take this, where is this? Okay, this is my, this is, okay, if I take IS also 1 e power minus 17, so what is this? IC is given by IS e power VBE by VT. This is VBE, which is, okay, now let me, okay, how much is IS? IS is 1 e power minus 17 multiplied by exponential to the power of 819 divided by 26, because both are milli, it will go off. Can you see now you have almost the same current? How much the current you have? You have a current of 478 microampere. Of course, you are getting 492. This is 478, which is not too far away from your actual value. So this assumption of VB is 0.7 is not true for all cases. Not true for all cases. You can see here also in the previous case, when you have it as 100 ohm, we assumed it as 0.7 as VP, and we found out IB and all those stuff. But the IB was supposed to be 43 milliampere with this assumption as 0.7, but it is not 0.7. How much you got? Suppose if I just replace this by 100 ohm, so how much is the value I'm getting? Let me rerun it. How much is VB? Can you see VB is a point? Okay, now this is with RC is equal to 100 ohm. Let me write what is VB. VB is how much? VB is 870.4. How much is VC? How much is VC? VC is 4.587 with IS as 1 into 10 power minus 17 ampere. How much is IC? How much is IC I'm getting? IC I'm getting as 4.12 milliampere. Let me just verify these values. Meaning these are the values of different parameter. Let me find out what is the expression of IC, or what is the value of IC using IS e power minus, sorry, it's not minus, VB by VT. It is 1 exponential minus 17 into exponential 870.4 divided by 26, close. Can you see now it is how much? 3.45 milliamperes. We are getting a current of, okay, let me just go back and see. This is 100K, this is 100, this is 5. Okay, let me rerun it. Let me see what is this. Okay, it is 41 point something, and this current is, okay, it is now 4.1, and this is how much? 870, and this is, okay, okay, VC is at 4.5. See now we have, because you can see there is a variation from this and this, so you are getting a simulation current of this, whereas actual current using this equation is coming out to be this. Since you can see I have put it as 870 point something, 870.4, so let me do 871 because it is so sensitive. Suppose if I make it 871, can you see this? So this will become a 1 or 2 milliamperes of okay, 1 or 2 millivolts of voltage. Suppose if I make it as 6, okay, if I make it as 8, can you see this comes out to be such a huge current. Now, don't think that okay, this 8.35 is too far away from this. Can you see from 870 millivolts to, suppose if I just make it 875, it's hardly a change of 5 millivolts. Can you see the 5 millivolts change will make a huge difference from 3.45 to 4.19 milliampere, meaning keeping the value of VBE stable is very essential. Meaning that's why these type of biasing is not used, because if the value of VBE changes by a very small minutes of millivolts, the IC changes enormously. So that's why. So we are not using these type of fixed bias where the current is now decided by only IB. So okay, you don't have a control on VB because this is not connected to ground through a resistor. So let us see in the next video what is the importance of having these potential divider bias in having a stable biasing for these transistors. You can see now it is 17K, this is 8K, 5K, and in the next case it is simply made as 170K, 80K, still it is 5K. Let us see what is the difference. So 17K, 8K potential difference voltage is same here also it is same, in spite of both are giving same voltage of 0.8. Which one is better? We'll just see that in the next video. So what I mean to say here is, we cannot simply assume this as 0.7 and then proceed. And of course nowadays nobody uses this type of fixed bias. So assumption of 0.7 as VBE and assuming this IC is equal to beta times IB is not true for all the cases. And this current of IC is very sensitive to VB. You can see if VB changes from, if it is 870 millivolts, it is coming to be 8.35. The moment this becomes 874 milliampere, then this will become 4.1 milliampere, almost 10% or 20%, 15% change in the current, increase in the current, because it is exponential to the VB changes. So that's why biasing of a transistor and keeping it insensitive to or immune to the temperature variations or variation of other parameters is very essential in electronics. Okay, we'll see in the next video the other potential divider biasing for the transistors.